Chapter 22, The Bipolar Transistor, page 374. The word transistor is a contraction of current transferring resistor. A bipolar transistor has two PN junctions. Two configurations exist for bipolar transistors: a p-type layer between two n-type layers called NPN, or n-type layer between two p-type layers called PNP. NPN versus PNP. Figure 22.1a is a simplified drawing of an NPN bipolar transistor, and Figure 22.1b shows the symbol that engineers use for it in schematic diagrams. The p-type or centered layer constitutes the base period. One of the n-type semiconductor layers forms the emitter, and the other n-type layer forms the collector. We label the base, the emitter, and the collector B, E, and C respectively. A PNP bipolar transistor has two p-type layers, one on either side of a thin n-type layer as shown in Figure 22.2a. The schematic symbol appears at Figure 22.2b. The n-type layer constitutes the base. One of the p-type layers forms the emitter, and the other p-type layer forms the collector. As with the NPN device, we label these electrodes B, E, and C. We can tell from a schematic diagram whether the circuit designer means for a transistor to be NPN type or PNP type. Once we realize that the arrow always goes with the emitter, we can identify the three electrodes without having to label them. In an NPN transistor, the arrow at the emitter points outward. In a PNP transistor, the arrow at the emitter points inward. Generally, PNP and NPN transistors can perform the same electronic functions. However, they require different voltage polarities, and the current flows in different directions. In many situations, we can replace an NPN device with a PNP device, or vice versa, reverse the power supply polarity, and expect the circuit to work in the replacement device if it has the appropriate specifications. Biasing. For a while, let's imagine a bipolar transistor as two diodes connected in reverse series. That is, in series, but in opposite directions. We can't normally connect two diodes together this way and get a working transistor, but the analogy works for modeling, technically describing the behavior of bipolar transistors. Figure 22.3a shows a dual diode NPN transistor model. The base is at the connection point between the two anodes. The cathode of one diode forms the device's emitter, while the cathode of the other diode forms the collector. Figure 22.3b shows the equivalent real-world NPN transistor circuit. NPN biasing. In an NPN transistor, we normally bias the device so that the collector voltage is positive with respect to the emitter. We illustrate this scheme by indicating the battery polarity in figures 22.3a and 22.3b. Typical DC voltages for a transistor's power supply range between about 3 volts and 50 volts, meaning that the collector electrode and the emitter electrode differ in potential by 3 volts to 50 volts. Page 376. In these diagrams, we label the base point control because the flow of current through the transistor depends on what happens at this electrode. Any change in the voltage that we apply to the base, either in the form of DC or AC, profoundly affects what happens inside the transistor and also what happens in other components that we connect to it. Zero bias for NPN. Suppose that we connect an NPN transistor so that the base and the emitter are at the same voltage. We call this condition zero bias because the potential difference between the two electrodes equals 0 volts. In this situation, the emitter base current, often called simply the base current and denoted current with subscript B, equals 0. The emitter base junction, which is a PN junction, operates below its forward breakover voltage, preventing current from flowing between the emitter and the base. Zero bias also prevents any current from flowing between the emitter and the collector, unless we inject an AC signal at the base to change things. Such a signal must at least momentarily attain a positive voltage equal to or greater than the forward breakover voltage of the EB junction. When no current flows between the emitter and the collector in a bipolar transistor under no signal conditions, we say that the device is operating in a state of cutoff. Reverse bias for NPN. Imagine that we connect an extra battery between the base and the emitter in the circuit of figure 22.3b with a polarity that will force the base voltage E, subscript B, to become negative with respect to the emitter. The presence of the new battery causes the EB junction to operate in a state of reverse bias. No current flows through the EB junction in this situation as long as the new battery voltage is not so great that avalanche breakdown occurs at the EB junction. In that sense, the transistor behaves in the same way when reverse biased as it does when zero biased. If we inject an AC signal at the base with the intent to cause a flow current during part of the cycle, the signal must attain, at least momentarily, a positive voltage high enough to overcome the sum of reverse bias voltage produced by the battery and the forward breakover voltage of the EB junction. We'll have a harder time getting a reverse biased transistor to conduct than we would have getting a zero biased transistor to conduct. Forward bias for NPN. Now suppose that we make EB positive with respect to the emitter, starting at small voltages and gradually increasing. The situation gives us a state of forward bias at the EB junction. If the forward bias remains below the forward breakover voltage, no current flows, either in the EB junction or from the emitter to the collector. But when the base voltage EB reaches and then exceeds the breakover point, the EB junction conducts and current starts to flow through the EB junction. The base collector junction of a bipolar transistor is normally reverse biased. It will remain reverse biased as long as the EB stays smaller than the supply voltage between the emitter and the collector. In practical transistor circuits, engineers commonly set EB at a small fraction of the supply voltage. For example, if the battery between the emitter and the collector in figures 22.3a and b provides 12 volts, the small battery between the emitter and the base might consist of a single 1.5 volt cell. Despite the reverse bias of the BC junction, a significant emitter collector current called collector current and denoted IC flows through the transistor once the EB junction conducts. In a real transistor circuit, such as the one shown in figure 22.3b, the meter reading will jump when we apply DC base bias to reach and then exceed the forward breakover voltage of the EB junction. If we continue to increase the forward bias at the EB junction, even a small rise in EB attended by a rise in the base current will cause a large increase in the collector current, IC. Figure 22-4 portrays the situation as a graph. Once current starts to flow in the collector, increasing EB a tiny bit will cause the IC to go up a lot. However, if EB continues to rise, we'll eventually arrive at a voltage where the curve of IC versus EB levels off. Then we say that the transistor has reached a state of saturation. It's running wide open, conducting as much as it possibly can, given a fixed potential difference between the collector and the emitter. PNP biasing. We can describe the situation inside a PNP transistor as we vary the voltage of the small battery or cell between the emitter and the base, and as a mirror image of the case for an NPN device. The diodes are reversed. The dual diode PNP model along with the real-world transistor circuit appear in figure 22.5. We can repeat the foregoing discussion for the NPN case almost verbatim, except that we must replace every occurrence of the word positive with the word negative. Qualitatively, the same things happen in the PNP circuit as in the NPN circuit. Top of page 378. Amplification. Because a small change in IB causes a large variation in IC, when we set the DC bias voltage properly, a transistor can operate as a current amplifier. Engineers use several expressions to describe the current amplification characteristics of a bipolar transistor. Collector current versus base current. Figure 22.6 is a graph of the way the collector current, IC, changes in a typical bipolar transistor as the base current changes. We can see some points along the IC versus IB curve at which a transistor won't provide any current amplification. For example, if we operate the transistor in saturation, shown by the extreme upper right-hand part of the curve, the IC versus IB curve runs horizontally. In this zone, a small change in the IB causes little or no change in IC, but if we bias the transistor near the middle of the ramped-up straight line part of the curve in figure 22.6, the transistor will work as a current amplifier. Whether we want a bipolar transistor to amplify a signal, we must bias the device so that a small change in the current between the emitter and the base will result in a large change in the current between the emitter and the collector. The ideal voltages for EB, the base bias, and EC, the power supply voltage, depend on the internal construction of the transistor and also on the chemical composition of the semiconductor materials that make up its N-type and P-type sections. Static current characteristics. We can describe the current carrying characteristics of a bipolar transistor in simplistic terms as the static forward current transfer ratio. This parameter comes in two flavors. One that describes the collector current versus the emitter current. When we place the base at electrical ground, symbolized HFB, and the other that describes the collector current versus the base current when we place the emitter at electrical ground, symbolized thus. The quantity HFB equals the ratio of the collector current to the emitter current at a given instant in time with the base grounded. For example, if an emitter of 100 milliamps results in a collector current of IC of 90 milliamps, then we can calculate thus: if IE equals 100 milliamps and IC equals 95 milliamps, then thus is the calculation: the quantity HFE equals the ratio of collector current to the base current at a given instant in time with the emitter grounded. For example, if a base current IB of 10 milliamps results in the collector current of IC of 90 milliamps, then we can calculate thus: alpha. We can describe the current variations in a bipolar transistor by dividing the difference in IC by the difference in IE that occurs when we apply a small signal to the emitter of a transistor with the base connected to electrical ground, or placed at the same potential as electrical ground. We call this ratio the alpha, symbolized as the lowercase Greek letter alpha. Let's abbreviate the words the difference in by writing D. Then mathematically we can define this equation. We call this quantity the dynamic current gain of the transistor for the ground base situation. The alpha for any transistor is always less than 1, because whenever we apply a signal to the input, the base bleeds off at least a little current from the emitter before it shows up at the collector. Beta. We can we get an excellent definition of current amplification for real-world signals when we divide the difference in IC by the difference in the current at the base, as we apply a small signal to the base of a transistor with the emitter at electrical ground. Then we get the dynamic current gain for the grounded emitter case. We call this ratio the beta, symbolized as the lowercase Greek letter beta. Once again, let's abbreviate the words, the difference as D. Then we have this equation. The beta for any transistor can exceed 1 and often does greatly. So this expression for current gain lives up to its name. However, under some conditions, we might observe a beta of less than 1. This condition can occur if we improperly bias a transistor. If we choose the wrong type of transistor for a particular application, or if we attempt to operate the transistor at a signal frequency that's far higher than the maximum frequency for which it is designed. Page 380 at the top. How alpha and beta relate. Whenever base current flows in a bipolar transistor, we can calculate the beta in terms of the alpha with the formula thus, and we can calculate the alpha in terms of the beta using the formula as seen. With a little bit of algebra, we can derive these formulas from the fact that at any instant in time, the collector current equals the emitter current minus the base current. That is, well, collector current equals the emitter current minus the base current. Real-world amplification. Let's look at figure 22C again. It's a graph of the collector current as a function of the base current, IC versus IB, for a hypothetical transistor. We can infer... Okay, I just got distracted. Let's look at figure 22.6 again. It's a graph of the collector current as a function of the base current, IC versus IB, for a hypothetical transistor. We can infer both HFE and beta from this graph. We can find HFE at any particular point on the curve when we divide IC by IB at that point. Geometrically, the value of beta at any given point on the curve equals the slope, rise over run, of a tangent line at the point. On a two-dimensional coordinate grid, the tangent to a curve at a point constitutes the straight line that intersects the curve at the point without crossing the curve. In figure 22.6, the tangent to the curve at point B appears as a dashed straight line. The tangents to the curve at points A and C lie precisely along the curve and therefore don't show up visually. As the slope of the line tangent to the curve increases, the value of beta increases. Point A provides the highest value of beta for this particular transistor as long as we don't let the input signal get too strong. Points in the immediate vicinity of point A provide good beta values as well. For small signal amplification, point A in figure 22.6 represents a good bias level. Engineers would say that it's a favorable operating point. The beta figure at point B is smaller. The curve slopes less steeply upward as we move toward the right than the beta figure at point A, so point B represents a less favorable operating point for small signal amplification than point A does. At point C, we can surmise that beta equals 0 because the slope of the curve equals 0 in that vicinity. It doesn't rise at all as we run toward the right. The transistor won't amplify weak signals when we bias it at point C or beyond. Overdrive. Even when we bias a transistor so that it can produce the greatest possible current amplification at or near point A in figure 22.6, we can encounter problems if we inject an AC input signal that's too strong. If the input signal amplitude gets large enough, the transistor's operating point might move to or beyond point B, off the coordinate grid, to the left, or both, during part of the signal cycle. In that case, the effective value of beta will decrease. Figure 22.7 shows why this effect occurs. Point X and Y represent the instantaneous current extremes during the signal cycle in this particular case. Note that the slope of the line connecting points X and Y is less than the slope of the straight line part of the curve at and near point A. When our AC signal is so strong that it drives the transistor to the extreme points X and Y, as shown in figure 22.7, a transistor amplifier introduces distortion into the signal, meaning that the output wave does not have the same shape as the input wave. We call this phenomenon nonlinearity. We sometimes tolerate this condition, but often it's undesirable. Under most circumstances, we will want our amplifier to remain linear or to exhibit excellent linearity, meaning that the output wave has the same shape as, although probably stronger than, the output wave. Page 381 at the top. When the input signal to a transistor amplifier exceeds a certain critical maximum, we get a condition called overdrive. An overdriven transistor operates in or near saturation during part of the input signal cycle. Overdrive reduces the overall circuit efficiency, causes excessive collector current to flow, and can overheat the base collector junction. Sometimes overdrive can physically destroy a transistor. Gain versus frequency. A bipolar transistor exhibits an amplification factor, gain, that decreases as the signal frequency increases. Some bipolar transistors can amplify effectively at frequencies up to only a few megahertz. Other devices can work into the gigahertz range. The maximum operating frequency for a particular bipolar transistor depends on the capacitances of the PN junction inside the device. A low junction capacitance value translates into a high maximum usable frequency. Expressions of gain. You've learned about current gain expressed as a ratio. You'll also hear or read about voltage gain or power gain in amplifier circuits. You can express any gain figure as a ratio. For example, if you read that a circuit has a voltage gain of 15, then you know that the output signal voltage equals 15 times the input signal voltage. If someone tells you that the power gain of a circuit is 25, then you know that the output signal power equals 25 times the input signal power. Alpha cutoff frequency. Suppose that we operate a bipolar transistor as a current amplifier, and we deliver an input signal to it at 1 kilohertz. Then we steadily increase the input signal frequency so that the value of alpha declines. We define the alpha cutoff frequency of a bipolar transistor, symbolized as Fa, as the frequency at which a alpha decreases to 0.707 times its value at 1 kilohertz. Don't confuse this use of the term cutoff with the state of cutoff that we get when we zero bias or reverse bias a transistor under no signal conditions! A transistor can have considerable gain at its alpha cutoff frequency. By looking at this specification for a particular transistor, we can get an idea of how rapidly it loses its ability to amplify as the frequency goes up. Beta cutoff frequency. Imagine that we repeat the above described variable frequency experiment while watching beta instead of alpha. We describe that beta decreases as the frequency increases. We define the beta cutoff frequency, also called the gain bandwidth product, for a bipolar transistor, symbolized as FB or FT, as the frequency at which beta gets down to 1. If we try to make a transistor amplify above its beta cutoff frequency, we'll fail. Figure 22.8 shows the alpha cutoff and beta cutoff frequencies for the hypothetical transistor on a graph of gain versus signal frequency. Note the scales of this graph are not linear and that the divisions are unevenly spaced. We call this type of plot a log-log graph because both scales are logarithmic rather than linear. Common emitter configuration. A bipolar transistor can be wired up in three general ways. We can ground the emitter for the signal, we can ground the base for the signal, and we can ground the collector for the signal. An often used arrangement is the common emitter circuit. Common means grounded for the signal. Figure 22.9 shows the basic configuration. Even if a circuit point remains at ground potential for signals, it can have a significant DC voltage with respect to electrical ground. In the circuit shown, capacitor C1 appears as a short circuit to the AC signal, so the emitter remains at signal ground. But resistor R1 causes the emitter to attain and hold a certain positive DC voltage with respect to electrical ground, or a negative voltage if we replace the NPN transistor with a PNP device. The exact DC voltage at the emitter depends on the resistance of R1 and on the bias at the base. We set the DC base bias by adjusting the ratio of the values of resistors R2 and R3. The DC base bias can range from 0 volts or ground potential to plus 12 volts, which equals the power supply voltage. Normally it's a couple of volts. Capacitors C2 and C3 block DC to or from the external input and output circuits while letting the AC signal pass. Resistor R4 keeps the output signal from shorting out through the power supply. A signal enters the common emitter circuit through C2, so the signal causes the base current, IB, to vary. The small fluctuations in base current cause large changes in the collector current. The current passes through resistor 4, producing a fluctuating DC voltage across it. The AC components of this voltage passes unhindered through capacitor C3 to the output. The circuit of figure 22.9 represents the basis for many amplifier systems at all commonly encountered signal frequencies. The common emitter configuration can produce more gain than any other arrangement. The output wave appears inverted in phase opposition with respect to input wave. If the input signal constitutes a pure sine wave, then the common emitter circuits shifts the signal phase by 180 degrees. Common base configurations. As its name implies, the common base circuit, figure 22.10, has the base at signal ground. The DC bias is the same as that for common emitter circuit, but we apply the input signal at the emitter instead of at the base. This arrangement gives rise to fluctuations in the voltage across resistor R1, causing variations in base current. These small current fluctuations produce large variations in the current through R4. Therefore, amplification occurs. The output wave follows along in phase with the input wave. The signal enters the transistor through capacitor C1. Resistor R1 keeps the input signal from shorting out to ground. Resistors R2 and R3 provide the base bias. Capacitor C2 holds the base at signal ground. Resistor R4 keeps the output signal from shorting out through the power supply. We get the output through capacitor C3. The common base circuit exhibits a relatively low input impedance and provides somewhat less gain than a common emitter circuit. A common base amplifier offers better stability than most common emitter circuits do. By better stability, we mean that common base circuit is less likely to break into oscillation, generate a signal of its own, as a result of amplifying some of its own output. The main reason for this good behavior is the low input impedance of the common base circuit, which requires the input signal to offer significant power to drive the system into amplification. The common base circuit isn't sensitive enough to get out of control easily. Sensitive amplifiers such as optimally biased common emitter circuits can pick up some of their own output as a result of stray capacitance between the input and output waves. This little bit of signal leakage can provide enough energy at the input to cause the whole circuit to chase its own tail. When positive in-phase feedback gives rise to oscillation in an amplifier, we say that the amplifier suffers from parasitic oscillation or parasitics, which can cause a radio transmitter to put out signals on unauthorized frequencies or make a radio receiver stop working altogether. Common collector configuration. A common collector circuit, figure 2211, operates with the collector at signal ground. We apply the AC input signal at the transistor base just as we do with common emitter circuit. The signal passes through C2 into the base. Resistors R2 and R3 provide the correct base bias. Resistor R4 limits the current through the transistor. Capacitor C3 keeps the collector at signal ground. Fluctuating DC flows through R1 and a fluctuating voltage therefore appears across it. The AC part of this voltage passes through C1 to the output. Because the output flows or follows the emitter current, some engineers and technicians call this arrangement an emitter follower circuit. The output wave of a common collector circuit appears exactly in phase with the input wave. The transistor exhibits a relatively high input impedance, while its output impedance remains low. For this reason, the common collector circuit can take the place of a transformer when we want to match a high impedance circuit to a low impedance circuit or load. A well-designed emitter follower circuit can function over a wide range of frequencies than a typical wire-wound transformer can. Okay, in my electronics binder, I see that in my printed material from over a year ago, I printed out some transistor definitions, which were meant to further explain Gibelisco's book. So I'm just going to read these into the video, and I can maybe refer to my notes. Okay, Chapter 22, Transistor Amplification. Zero bias. A lack of voltage, current, capacitance, or other input which is applied to a component or device to establish a reference level for its operation. Emitter base junction. Diffusion of charge carriers across emitter and base. Cutoff. Cutoff is a state of negligible conduction that is a property of several types of electronic components when a control parameter, voltage or current, is lowered or increased past a value, the conduction threshold. Forward biased. When a voltage is applied across a diode in such a way that the diode allows current, the diode is said to be forward biased. When voltage is applied across a diode in such a way that the diode prohibits current, the diode is said to be reverse biased. Collector current. A small current leaving the base is amplified in the collector output. This is a PNP transistor. That is, a PNP transistor is on when its base is pulled low relative to the emitter. In a PNP transistor, the emitter base region is forward biased, so holes are injected into the base as minority carriers. Saturation. Saturation in electronics refers to maximum beyond which the system becomes unstable. If a device reaches its maximum voltage when a certain amount of current is gives as input, then the amount of current is known as saturation current, and for voltage it's vice versa. Current amplifier. An amplifier, electronic amplifier, or informally amp, is an electronic device that can increase the power of a signal, a time-varying voltage, or current. An amplifier functions by taking power from a power supply and controlling the output to match the input signal shape but with a larger amplitude. In this sense, an amplifier modulates the output of the power supply based on the properties of the input signal. An amplifier is effectively the opposite of an attenuator. While an amplifier provides gain, an attenuator provides loss. Characteristics of transistors from a random website. An important characteristics of a trans is its beta or current amplification factor, which is expressed as HFE, static forward current transfer ratio, or HFE, small signal forward current transfer ratio. Both relates to the grounded emitter configuration. Beta is the ratio of the collector current to its base current. Therefore, if the base current of 1 mA causes the collector current to rise 50 mA, the beta is 50. Typical junction transistors, beta is in the range of 10 to several hundreds. Alpha is the ratio of collector to its emitter current. Alpha equals the current of the collector divided by the current of the emitter. It is expressed as HFB, static forward current transfer ratio, or HFB, small signal forward current transfer ratio. The smaller the base current, the closer the collector current comes to equal with the emitter current, and the closer alpha comes equal to 1. Typical value of alpha for junction transistor is between 0.92 and 0.98. The collector current depends on the emitter current and is independent of the collector voltage. The separation between the curves is quite uniform, which means that almost distortionless output can be obtained over the useful operation range of the transistor. Static forward transfer ratio. Static forward current transfer ratio. Ratio of collector current versus emitter current when we place the base at electrical ground. Gain. The gain of a bipolar transistor normally refers to forward current transfer ratio, either HFE in parenthesis beta for static ratio of IC divided by IB at some operating point, or sometimes HFE, the small signal current gain, the slope of the graph of IC against IB at a point. HFB, C gain, HFE, C gain. Dynamic current gain. The dynamic current gain, A1 for a common emitter transistor circuit equals the change in collector current for a given change in base current with the collector to emitter voltage drop held constant. Operating point. In electronic engineering, establishing an operating point is called biasing. Biasing in electronics means establishing predetermined voltages or currents at various points of an electronic circuit for the purpose of establishing proper operating conditions in electronic components. Many electronic devices, such as transistors and vacuum tubes, whose function is processing time-varying AC signals, also requires a steady DC current or voltage to operate correctly. A bias. Distortion. Distortion in electronics. Undesired change in an electric signal waveform as it passes from the input to the output of some system or device. In an audio system, distortion results in poor reproduction of recorded or transmitted sound. Nonlinearity. In an electric circuit, a nonlinear element or nonlinear device is an electrical element which does not have a linear relationship between current and voltage. A diode is a simple example. The current I through a diode is a nonlinear function of the voltage V across its terminals. Low junction capacitance. Low junction capacitance, Schottky diodes, high current density, and low forward voltage drop means less wasted power compared with ordinary PN junction. Maximum usable frequency. Not a great definition I found, but from somewhat unrelated book. Above the maximum usable frequency, these atoms don't have time to switch positions, they just vibrate around one stable position. I think this concept refers to loss or wasted power. I don't know what I meant. Alpha cutoff frequency. The alpha cutoff frequency is determined in terms of the three major contributions: base region transport cutoff, emitter cutoff due to the emitter capacitance, and the collector cutoff due to the base resistance and the collector capacitance. Beta cutoff frequency. Beta cutoff frequency, FT, is the frequency at which common emitter small signal current gain falls to unity. Unity gain. A unity gain amplifier is an electronic amplifier circuit that doesn't amplify. In other words, it has gain of 1. The output voltage in a unity gain amplifier is the same as the input voltage. The gain bandwidth product for an amplifier is the product of the amplifier's bandwidth and the gain at which the bandwidth is measured. Common emitter circuit. In electronics, a common emitter amplifier is one of 3 basic single-stage bipolar junction transistor amplifier topologies, typically used as a voltage amplifier. In this circuit, the base terminal of the transistor serves as the input, the collector is the output, and the emitter is common to both. For example, it may be tied to ground, reference, or power supply rail, hence its name. The analogous FET field effect transistor circuit is the common source amplifier, and the analogous tube circuit is the common cathode amplifier. Signal ground. The difference between the two grounds is what they are used for. Signal ground provides a reference to which all signals in the device are compared against. Internal circuitry detects those levels and interprets them into useful values. Chassis ground is used more for shielding and grounding. Common base circuit. The current gain of a common base amplifier is always less than 1. The voltage gain is a function of input and output resistances, and also the internal resistance of the emitter base junction, which is subject to change with variations in DC bias voltage. Break into oscillation. Amplifiers without compensation are not stable below some specified minimum gain and can easily break into oscillation as shown.